In this video, we present our paper, Alleviating Foreground Sparsity for Semi-Supervised Monocular 3D Object Detection. Monocular 3D object detection is a challenging task due to a lack of explicit 3D measurements in monocular images. As such, the performance of existing monocular 3D object detectors markedly lags behind their LiDAR-based counterparts. On the other hand, semi-supervised learning allows making use of abundant unlabeled data for training. Data of other modalities such as LiDAR can also provide more 3D-aware and complementary knowledge for monocular detectors. Therefore, in this paper, we design a semi-supervised learning framework, utilizing large amounts of unlabeled data to boost an off-the-shelf monocular 3D object detector. Also, we propose to inject LiDAR-domain knowledge to a monocular detector via knowledge distillation. To begin with, we point out that existing methods suffer from two types of foreground sparsity problems. First, driving scenes may contain only a few or even no objects of interest. This can lead to inefficiency in the overall training due to insufficient supervisory signals. Second, the foreground objects become even more sparse in the bird's eye view feature space, and their beneficial supervisory signals can be overwhelmed by a significant amount of irrelevant background signal. This also results in inefficient training, especially in existing cross-modality knowledge transfer-based approaches. In this work, we make two designs to tackle both types of foreground sparsity problems. Our framework, ODM3D, is capable of utilizing unlabeled data whilst injecting additional LiDAR-induced knowledge into a monocular 3D object detector. ODM3D follows a teacher-student paradigm, where the teacher is a LiDAR-based 3D object detector, and the student is a monocular 3D object detector. Through our design, we wish to improve the student monocular detector by the stronger, more 3D-aware knowledge of the LiDAR-based teacher. In our experiment, we use the second detector as the teacher, and CADDN as the student. During training, the pre-trained teacher is fixed. It generates predictions for both labeled and unlabeled LiDAR samples, which are used to supervise the student. Knowledge distillation is carried out at both the feature level and the response level, both in the BEV space. At inference, the teacher is discarded, and the student is deployed as a standalone monocular detector. ODM3D incorporates two dedicated designs to address each of the two foreground sparsity problems mentioned earlier. For foreground sparsity in the BEV feature space, we use the point occupancy status within the LiDAR point cloud space to guide cross-modal distillation. The intuition is that a point cloud voxel is more likely to be part of an object if it contains LiDAR points. The occupancy map is obtained by first projecting the voxelized point cloud to BEV, followed by a pixelization operation to match the resolution of the BEV feature. Within the obtained BEV occupancy mask, a pixel with a value of 1 indicates that at least one point has been projected into that location, whereas a zero-valued pixel means no point has been projected into that location. This occupancy mask is used to guide both feature and response distillation in the BEV space. To address object sparsity in the training scenes, we design a joint LiDAR RGB data augmentation strategy. Specifically, we first extract objects from all training samples into a database. For labeled training samples, we simply use the ground truth labels to extract the objects. For unlabeled samples, we use predictions by the pre-trained teacher to extract objects. During training, we randomly sample objects from the database for each training scene. We then paste each sampled object's RGB patch into the image of the current scene. Meanwhile, we also paste each sampled object's points into the corresponding point cloud of the current scene. Next, collision tests are conducted to ensure that pasted objects do not severely occlude any existing objects in the image. In existing methods, the IOU has been used as a de facto measure of the extent of occlusion for box collision tests. However, we find that IOU is neither 3D aware nor occlusion aware, which leads to severe or even complete occlusion of objects after pasting, thereby harming the training. To overcome the limitation of IOU, we propose OAIS, Occlusion-Aware Intersection Score, which takes the pairwise depth relationship into account. OAIS is computed as the intersection area of two boxes divided by the area of the box with a larger depth value. These examples show how OAIS successfully indicates severe and complete occlusions where IOU fails. Here we show some visualizations of training scenes augmented by the proposed cross-modal augmentation. In these figures, orange points and boxes denote pasted objects. Next, let's move on to the experimental results. On the popular KITTI 3D object detection dataset, our method achieves the best performance, surpassing all previous methods, supervised or semi-supervised, on both validation and test sets, and on both APBEV and AP3D metrics. Among semi-supervised approaches, our ODM3D also yields the largest relative improvements over the base detector. On the car objects of the KITTI test set, ODM3D boosts the base monocular detector CADDN by around 50% on average. We also conducted an extensive set of ablation experiments, and validated that each of our design choices is effective. For more details, please refer to our paper. And some visualizations. We can notice that ODM3D more precisely detects occluded objects, objects in shadow, as well as far-away objects. And some more visualizations. To wrap up, in this work we proposed ODM3D, a novel semi-supervised learning framework for monocular 3D object detection. ODM3D employs LiDAR occupancy guidance for better LiDAR to RGB knowledge transfer. It also develops a more effective cross-modal scene augmentation strategy named CMU to enrich supervisory signals. Both designs effectively mitigated the two types of foreground sparsity problems we previously identified. Finally, benefiting from our designs, ODM3D successfully exploits large amounts of unlabelled data and LiDAR data to achieve new state-of-the-art monocular 3D object detection results. And that concludes this presentation. Thank you for your attention.